This is Mrs. Cribb, and we're going to be covering colligative properties now. So pull out your notes for chapter 12, and we're going to flip back and forth between the Prezi and the notes themselves, just so I can look at some of the videos, not videos, but pictures. So a colligative property is a physical property of solution that depends only on the number of particles present without regard to type. These include boiling point, freezing point, vapor pressure, and osmotic pressure. Now, what that means is it's counting the number of particles. It doesn't matter what kind they are. And the colligative properties change depending on what number of particles you have. Vapor pressure depression. This is the first one. At the surface of a solution, solute particles. Now remember, solute particles are what you're dissolving. Fill positions that normally occupied by solvent molecules. If the solute is less likely to become a gas or less volatile, now notice that. Less likely to become a gas means less volatile, or less volatile means how likely it is to become a gas. So connect those two, the definition for volatile and what it means. So if the solute is less likely to become a gas than the solvent, the vapor pressure will be lowered. All right, so there's a picture here. Then it goes on to say a mole of sodium chloride added to a liter of water would lower the vapor pressure more than adding a mole of sugar, because sodium chloride breaks apart into sodium, Na, and chlorine, Cl. Now let me go back to the notes for a second so we can fill that part in. So here we are on the notes, and we would say sodium breaks apart into sodium, Na with a plus sign, and chlorine, Cl minus. So this is ionic. Sodium chloride is ionic. Okay, metal, non-metal, ionic. And so those break apart into complete ions. A mole of sodium chloride added to water would lower the vapor pressure more than adding a mole of sugar. Now there's sugar. Sugar molecules don't break apart into lots of pieces, but the ionic ones do, because it breaks it now. And then AlCl3, which is this right here. Now notice Al, and then there's 3 chlorines, would lower the vapor pressure more than sodium chloride because it breaks apart into 1 aluminum that has a +3 charge and 3 chlorine ions that have a -1 charge. So AlCl3, this molecule, breaks apart into 4 pieces. Okay? Sodium chloride, excuse me, breaks apart into 2 pieces. Sodium and chlorine. But sugar doesn't break apart. So it's one. The sugar molecule stays as one unit. Okay? So the more pieces that you have, the lower the vapor pressure is going to be. All right, so before I go down and fill in these formulas, let's go back to our Prezi. So now you know what to put in those blanks. Now this is the first picture. This shows you a pure liquid like water. And there's liquid water molecules, and then there's gaseous water molecules on top. And those gaseous water molecules on top are the vapor. So that's the vapor pressure, the vapor that's pushing down on the liquid. And then of course we have the atmospheric pressure pushing down on the vapor. And that's important when we get to boiling point. Now here we have a solute, and I wish I could write on this picture, but the solute are the red particles. And they're filling some of the positions where the blue particles are. So basically they're blocking some of the blues. Here the blues are free to come to the surface and turn into a gas. But here the blues come up and they might get blocked by a red and stay back down. So they can't come up and become a gas because the red particles are in the way. So because the red particles, the solute particles, are blocking the blue liquid from becoming a gas, the amount of vapor on the top goes down, so the vapor pressure is lowered. Remember, the red particles, the solute particles, block the blue ones, so they can't escape. Only these here can escape and become gas particles. So it lowers the number of gas particles that can be created. That also lowers the vapor pressure. Okay? And we all went through this already. And that brings us to the boiling point elevation. Solute particles lower vapor pressure, that's what we just said, and thus raise the boiling point because it takes higher temperatures for the vapor pressure to equal the atmospheric pressure. Remember, that's the definition of boiling. When the vapor pressure going up equals the atmospheric pressure going down, a liquid can boil. But if the vapor pressure has gotten smaller, then the only way to increase the amount of vapor is to heat the liquid up even more to make more vapor escape. So a lower vapor pressure means you have to raise the boiling point you have to raise the temperature in order for things to boil. So the boiling point goes up. The first formula you're going to write is this. Write it just like that. And I'm going to go back to the notes for a moment and tell you what all those pieces mean. So let me go pull the notes up. So you notice I didn't write it here. But you will have these formulas in your reference chart. So let's see, how did I write that one this time? Delta T sub B, which is the change in the boiling point, is I K sub B M. All right, now I'm going to show you in the reference chart. I think this is it. Yeah. Delta T sub B equals I K sub B M. That's the first formula that you have. And if you want to write on the reference chart what all those mean, I'm okay with that. So let's go back to our notes. Now what does this all mean? Delta T sub B is the change in, remember that this symbol right here, the triangle always means the change in. So that's the change in the boiling point. Okay? I equals a particles count. It's a particle count, how many pieces that things fall apart into. Pieces. So up here we had aluminum chloride. We had 1 aluminum and 3 chlorine. So 1 plus 3 is 4 pieces. The I value would have been a 4 for that. Okay, now this only works for ionic because this is still ionic. Metal, non-metal, ionic, the I value you have to figure out by looking at all the ions. You have 1 aluminum ion and 3 chlorine ions. For sodium chloride, it's also ionic. So 1 chlorine and 1 sodium and 1 chlorine, so 1 plus 1 is 2. So 2 would have been the I value, the number of pieces. But sugar doesn't fall apart, and sugar is covalent. Covalent molecules don't fall apart, so the I value is 1 for the covalent molecules, okay? So for sugar and covalent molecules, I value is 1. For ionic compounds, you have to count the ions, and that's the I value. All right, so the I is that. The Kb is the mole boiling point constant. The mole boiling point constant is K sub B. Is the temperature elevation that 1 mole of particles, molecules, atoms, or ions, in 1 kilogram of water will cause. So it's the mole boiling point constant, 1 mole of particles in 1 kilogram of water will cause. The more concentrated a solution is, the greater the boiling point elevation will be. The more concentrated, that means the more particles you dissolve, the more spots are blocking it. So let's draw that picture, and I really do want you to have this idea in your notes, okay? Here's a picture, and this is full of water molecules, okay? And these water molecules want to escape, and they're very volatile. They turn into a gas very easily. But this thing is also full of solute particles. And those solute particles are taking up space inside the dissolved liquid. All right, so now my water wants to escape and become a gas. But some of it hits that solute particle and falls back down into solution. And it doesn't get to dissolve. It doesn't get to evaporate. Some of them here on the outsides, they're the ones that escape. The ones that are not being blocked. So because the solute particles are blocking it, the vapor pressure goes down. Okay? If the vapor pressure goes down, the boiling point has to go up. Because what is boiling point? We did this before. Boiling is when the vapor pressure equals the atmospheric pressure. So in order for it to boil, the amount of vapor I create has to equal the amount of pressure the atmosphere is pushing down. So the vapor pressure is trying to push up. And if I don't have enough vapor pressure pushing up, I've got to make this liquid get even hotter. Okay? Because if I make that hotter, more of it will escape. Think about that carefully. Now, the second formula that you're going to need to write is delta T sub B, which is the change in the boiling point, is equal to the final boiling point minus the initial boiling point. Or you could say the temperature FB, final boiling point minus the temperature IB. Or you could say the delta T sub B equals the second boiling temperature minus the first one, number 1. This formula is also on your chart, your reference chart. And see here I pointed to delta T sub B and then the other formula, delta T sub B, or you could new minus old, new minus original boiling point. Okay? That's what that could be as well, new minus original. So you can write the same formula in multiple ways. So we could write it like that. Let's do that other way. Delta T sub B could be the new boiling point minus the original boiling point. If you want to change those subscripts to help you to remember it, I'm fine with that. Okay? All right. So now how do we use this? Let's go ahead. What is the boiling point of acetone? So really they're asking for the new boiling point, okay? And acetone is covalent. Now that's important because if it's covalent, I know something automatically. When 0.5 moles of naphthalene, that's what naphthalene is added to 1 kilogram of acetone, the molal boiling point constant, that's the K sub B, that's what that is this number. All right, so let's write out our formula. We're dealing with boiling point, so delta T sub B equals I K sub B M. Now what is M? M is the molality, and I didn't specify that up here. It's a lowercase m, so M is the molality. And remember what molality is? Moles of solute over kilograms of solvent. That's what little m means. So here, molality. Molality is the moles of solute over kilograms of solvent. Now you need to be filling in your notes and drawing pictures. I hope you do that. All right, so I need to know the change in the boiling point first, and then I can figure out what the new boiling point is. The new boiling point minus the original boiling point. Second minus the first is the change. All right. Now, I'm not going to expect you to know the boiling point of acetone, so this is something that we'll have to look up. All right, what is the I value, first of all? Well, I told you it's covalent, and for all covalent things, the I value is 1. That's the number of things it falls apart into. The K sub B was given to you right here. So 1.71 degrees Celsius per molal, not moles, per molal. If it was moles, it would say MOL. It's not moles, it's molality. All right, so what's the molality? Well, I'm going to have to figure that out because I don't have the molality. They gave me some stuff though. What is molality? Little m is the moles of the solute divided by the kilograms of the solvent. Now, how do I know that? Well, I know it because I've been doing it a million times, but you know it too by this formula, moles of solute over kilograms of solvent, right here. All right, so moles of solute, they gave me that. Okay, 0.500 moles of naphthalene divided by 1 kilogram of acetone. Acetone is a solvent, 1.00 kilograms. Well, this is an easy one, 0.500 molal, the little m, because 5 divided by 1 is the same thing. 0.5 divided by 1 is 0.5. Okay, the significant figures are 3 significant figures. So the answer over here is 0.500 little molal. And so now I'm able to calculate the change in the boiling point by just putting these numbers in. All right, and I'll put those numbers in for you, or calculate. Now I put the number in, 0.855. And we have to look at significant figures. Don't use this as a sig fig because this is a definition. So this is what you'd use, and that's 3 sig figs. Notice that the molality unit cancels, so the degrees Celsius is the only unit left, which is kind of good because that's temperature. But that is the change in the boiling point. It is not what is the boiling point. It's how much does the boiling point change. Now I need to know the new boiling point. So I got to use this number in this spot. I got to use this number here. So now I'm going to say 0.855 degrees Celsius is the change in the boiling point. I want to know the new boiling point, but that means I need to know what is the original boiling point of the solvent. Okay, what was the solvent? Acetone. You have to know that. And I know that because they said if they tell you the molal boiling point constant of something, that's the solvent. The other thing is the thing they tell you the moles of, that had to be the solute. Because look, moles of solute. So the solvent here is acetone. Well, I don't know the boiling point of acetone. So if I look on here, that's what this is for. The molal freezing and boiling point constants. So I find acetone, there it is. And I'm talking about boiling point. So the original boiling point of acetone, look, there's acetone. That's the freezing point of acetone, negative 95.4. And this is the boiling point of acetone, 56.2. So 56.2 degrees Celsius is my original boiling point. Do you understand? These are the original boiling points before you add solute. When you add solute, things change. So, I forgot it already. 56.2. Okay, 56.2. So I have to write that here. That's my original boiling point. Now I'm going to add 56.2 to both sides. And you don't have to write this part out. I'm just reminding you of the math process. So what the new boiling point is, and that's what and notice that the new boiling point should always be bigger than the original boiling point. It's called boiling point elevation for that reason. All right, when I add that together, I get 57.055 degrees Celsius, boiling point elevation. All right, how many sig figs should this have? Well, we got to evaluate. We're subtracting, or adding in this case. This only goes to the 10th place, so I can only go to the 10th place. Remember, that's the least precise. So it's 57.1, because that 5 causes the 0 to go up to 1 degrees Celsius. That is your new boiling point. The original boiling point was 56.2. By adding some solute to it, in this case called naphthalene, it's now 57. It has to get hotter to boil now. Okay. Something to remember, ionic compounds break apart into ions in solution, but covalent compounds separate into molecules. You will need to multiply the number of moles of particles by the number of released ions. All right, the number of moles times the number of ions. This results in particle molality. Sodium chloride would be multiplied by 2, so its I value is a 2, because you get 1 sodium ion and 1 chlorine ion. Aluminum chloride would be multiplied by 4 because you get 1 aluminum ion and 3 chlorine ions. Covalent molecules do not break apart, so you multiply by 1. Those are the I values. When I say multiply by something, it really is the I value. Covalent molecules, the I value is 1. All right, let's do this next one. If 425 grams of magnesium chloride are added to 675 grams of hot water, what is the boiling point? This is the new boiling point. All right, and we have to figure out which one is the solvent and the solute. So in here, the solute is what you have less of. Okay, so the solute here is the 425 grams of magnesium. Now magnesium and chlorine, and so magnesium I think is a +2. Yeah, and chlorine's a -1, so swap and drop. MgCl2. Okay, the solvent is water. We have 675 grams of water. Okay, so we have to figure out what to do in order to figure out molality. Molality is what's used in this formula. First of all, this is the solute. It's ionic, so we have to ask, is it ionic? Yes. So what is the I value then? Well, 1 magnesium, 2 chlorines. 1 plus 2 is 3. 3 is the I. We need to know what the value of the I is. And that's if it's ionic. If it's covalent, the I value is automatically 1. All right, so this is the solvent. We have to turn that into kilograms. So we divide by 1,000. 1, 2, 3. So that's 0.675 kilograms. And I need that for molality. All right, now it's asking me about boiling point. So what formulas do I use? First, I use delta T sub B equals I, K sub B, molality. The I is a 3, right there. We just figured that out. The K sub B, well, and I gave it to you, the boiling point constant of water. Now, if I give you the boiling point constant of it, that thing is the solvent. There's the value. So 0.512 degrees Celsius per molal. But now I need the molality. And little m is molality. And molality is moles of solute over kilograms of solvent. All right, so I turned the solvent into kilograms already, 0.675 kilograms. I've got to turn the solid, the mass, into moles, right here, the mass into moles, before, so I can solve for that. So 425 grams of magnesium chloride. You use the molar mass to figure out how many moles you have. So I got to figure out the molar mass. Magnesium, chlorine, 2 times 35.45. Magnesium, I'm going to have to look that up. So hold on one second. Looked it up. Magnesium is 24.31. So 2 times 35.45 for chlorine is 70.90. Add them together. I get 95.21 grams per mole. So I put that up here. The grams on the bottom, the moles on the top, because I'm trying to figure out how many moles. The units cancel. So 425 divided by 95.21, I just multiplied it. That would have been a bad mistake. Divided by 95.21 is 4.4638. I look at significant figures, 3 sig figs, 1, 2, 3. That causes it to stay down. I don't round it up. So it's 4.47 moles. So that's what this is. Molality, 4.47 moles. Now I can calculate it. The number of moles divided by the kilograms. 4.47 divided by the kilograms is 0.675. I got 6.62. And the sig figs is right. 6.62 little m, molality. So 6.62 little m for molality. All right, now that I know the molality and I know the I value in the case of B, I should be able to cancel out the little m's and come up with the change in the boiling point. I'm going to do that real fast. I went and multiplied this. Now, I will tell you this too while I'm at it. This formula right here is not the same one the book uses. The book doesn't use an I value. It incorporates the I value into the molality to create the particle molality. Right here where they multiply it by it, but I like to use the I value because it reminds you to double check. So this is the one we're going to be using and not the one in the book, but it's still example 12.9. We still get the same answer. So now I have the change in the boiling point, and I have to check for sig figs, and I don't use the I value because the I value is something you just count. I don't use the the molal constant. I use this one. That's the only thing I calculated. That's 3 sig figs. So that's at 10.2 degrees Celsius. That's the change in the boiling point. Now that I have the change in the boiling point, I can figure out the new boiling point. So I have to use the second formula. Delta T sub B is the new boiling point minus the original boiling point. Okay, so I use this. This is equal to 10.2, so I use it here. 10.2 degrees Celsius is the new boiling point. Okay, what's the original boiling point of water? You shouldn't have to look this one up. The original boiling point of water is 100 degrees Celsius. So I add 100 to both sides so that the new boiling point is 110.2 degrees Celsius. Now notice how much that went up. By adding 425 grams of magnesium chloride, the boiling point of water increased 10 degrees. Boiling point elevation, these new boiling point, should always be higher than the original boiling point. Okay, hope you got that. Now let's move on to the next example. What is the molality? This time it's asking for the little m of a solution of sodium chloride. All right, that's ionic. So we're going to figure out the I. So the I value is equal to sodium plus chlorine, 1 plus 1. The I value is 2. In water, so that's the solvent. If the solution has a change in the boiling point, okay, it has a change. That's the delta in the boiling point. So it's the change in the boiling point is 0.400 degrees C. Okay, do you see that this time they did not give you the original boiling point or anything else? They gave you the change in the boiling point. So let's, our formulas then, we have a delta T sub B is I, and it's talking about boiling point, K sub B M, and delta T sub B is the new boiling point minus the original boiling point. All right, what did they give me? You should always do this and evaluate. They gave me the change. So that number can be used here and here. So 0.400 degrees Celsius. And the question is asking me for the molality. All right, well then I don't really need this one over here. I can just put this one here. 0.400 degrees Celsius equals, I told you the I is 2. I need the boiling point constant for water because water is the solvent. The solvent is where you get the K sub B. The boiling point constant comes from the solvent. And then they want M, molality. So I need to figure out what the boiling point constant of water is. I get that off my reference chart. So water, there's the freezing point of water. Now look, I even gave you the boiling point. I shouldn't have given you those two. The freezing point is 0 degrees Celsius. The boiling point's 100. The boiling point constant, the K sub B, is 0.512 right here on your reference sheet. So that's what I need to use when I'm doing this. So 0.512 degrees Celsius per molal. All right. Oh, and we know the I is 2, so I could have just gone ahead and wrote in. I need to write in the 2 right here. Now we're solving for M. That's the only unknown. The number of moles, the molality in this case rather. So I'm going to isolate my little m right here. So I'm going to divide this side by 2 and this side by 2 and divide this side by 0.512 degrees Celsius over molal and divide this side by 0.512 degrees Celsius over molal. So this is the whole thing cancels. So my molality is all by itself, and my degrees Celsius cancel. There's one right here and one right there. So molality is the unit that's left, which is what I want. So now I just 0.4 divided by 2 divided by 0.512. So let's do that. 0.4 divided by 2 divided by 0.512, and I get 0.3906 molal. Okay, and I got to figure out sig figs. So this is the only measured value they really gave me. 3 significant figures. 1, 2, 3. 0.391 molal. There's my answer. So I didn't need to use this formula at all this time, even though they gave me this. I could have figured out the new boiling point though, because the new boiling point would be the original boiling point, which is 100. Well, not 1,000, 100. And just add it to it, and I would have been able to just figure out the new boiling point was 100.400 degrees Celsius. It wasn't a big change, but it was a change. All right, that brings us to the freezing point depression, and that's a very, very similar thing. And I'm going to give you the formula. I'm going to show you the formula on your reference sheet. There it is, negative I, K sub F. So the freezing change in the freezing point is negative I, K sub F, little m for molality. So it's almost identical to the boiling point. So write it up here. Negative I, K sub F m equals the change in the freezing point, the delta T sub F. So delta T sub F is the change in the freezing point. And the freezing point should always go down. It's boiling point depression. So freezing point depression. The boiling point goes up and the freezing point goes down. So it has to get even colder. The Molal freezing point constant is just like the boiling point constant, except it has an F instead of a B. And then you also need to do the change in the freezing point is equal to the new freezing point minus the original freezing point. Or the second one minus the first, or whatever. You can use whichever formula you want. These are all worked exactly the same way as the boiling point. How much will the freezing point of phenol, there's my thing, that must be the solvent, change if 4 moles of naphthalene, which is covalent, if it's covalent, I is 1, are dissolved in 2 kilograms of phenol. So this is definitely the solvent. The solvent is where you get your K sub F, your freezing point constant. So let's write the formula. Delta T sub F equals a negative I K sub F M. Again, this formula is not used in the book. It's one I use from a different resource. So use this one, please. All right. So let's see here. What do I know? I know I. I is 1. So it's a negative 1. The K sub F for phenol. That's the solvent. I'm going to go look on my reference sheet and see if I see it. Phenol. All right. K sub F, 7.27 degrees Celsius per molal. So I'm using my reference sheet, 7.27. 7.27 degrees Celsius per molal. All right, what's the molality? I don't know. What is molality? It's moles of solute over kilograms of solution. Solvent. Careful. All right, they gave me the moles of the solute, 4. And they gave me the kilograms of the solvent, 2. So this is just 2, little m, 2 molal. There's my 2.00 molal. 3 significant figures on the top and bottom. And so the change in the freezing point can now be calculated, and we can cancel out the units of the m's. So we have just degrees Celsius. So I'm going to pull the calculator up and do that one real quick, just because I don't know which is faster. All right, let's see. 7.27 times 2. 14.54. Now, what about sig figs? This is a 3 sig fig number. We don't use that because that's a definition. So 14.5 degrees Celsius is the change in the freezing temperature. Now, is that what will the freezing point of phenol change? How much will it change? Key word right there, change. So that is the answer. It will change by 14.5 degrees. It will go down, and I have to do the negative sign, so it really is negative 14.5. Don't forget that. That negative sign is super important. It will go down 14.5 degrees Celsius, or the change is a negative 14.5 degrees Celsius. Okay? All right. So that's that one. Now, the negative sign is important. I didn't carry it right here, and I almost messed up. The reason I remembered it is because freezing points should always go down, and that's always going towards a negative end. Think about your 4 quadrants here. It's positive on the top and negative on the bottom. So the freezing point should always be headed towards the negative end. So you have to have that negative sign. The change in the freezing point is always going down. It goes down a positive amount, or it changes a negative amount. Okay, I hope you got that one. The more ions or particles a solute breaks down into, the lower the freezing point will be. Calcium chloride, that would be ionic. So lowers the freezing point more than sodium chloride, which is also ionic, because calcium has 3 ions instead of 2. See, 1 calcium plus 2 chlorines, that's a 3. So the I is equal to a 3. So it's going to multiply everything by 3. Here the I is equal to a 2. It's only multiplying everything by 2. So we're going to compare the freezing points of a 3 molal calcium chloride solution and a 3 molal sodium chloride solution. And both of them are in water. So all we're going to do here is just compare the freezing points of these, okay? All right, we got to use the delta T sub F equals a negative I K sub Fm for both of them. Delta T sub F is a negative I K sub Fm. There's not going to be a lot of work. We're just comparing here. So the I, and this side over here, we'll do calcium chloride on this side, and we'll do sodium chloride on this side. The I here is a negative 3. The K sub F for water, I have to go look that up. Water, K sub F is 1.86. That's for freezing point, 1.86. So 1.86 degrees Celsius per molal. And it told me the molality too. It's 3 molal. So the molality for both of these guys is the same. I'm going to set it up over here. Delta T sub F equals a negative I for sodium chloride. It's a 2, so negative 2. See, here the I is a 2. Here the I is a 3. Because of the number of particles it falls apart into. The K sub F is identical because they're both in water. And the molality is identical because they said so in the problem. So now all we got to do is cancel out our units, and we'll know how much the temperature changes for each of them. Okay, let me do that for you real quick. Did the work for you. It's 3 sig bigs for in both cases because the 3.00 molal. So for calcium chloride, the temperature would go down by a negative 16.7 degrees. For sodium chloride, it go down by a negative 11.2. This is the change at the freezing point. But if you do delta T sub F is the new freezing point minus the original freezing point, the change is negative 16.7. The new freezing point would be, and the original freezing point of water is 0. So you see add 0 to both sides so that the new freezing point is the same as the change in this case. Now that only works for water because water is the only thing that freezes at 0 degrees Celsius. Otherwise you have to put a number there. So same thing over here. The new freezing point is a negative 11.1 degrees Celsius. So what do you notice about that? The more particles that breaks apart into, the I values, the particle count, the more it changes the freezing point. And we use this in order to melt the water, the ice on the roads. We put salt on there so that the water has to freeze at a lower temperature so that we end up turning the water back into a liquid and we can clean up our roads that way. All right, that's boiling point and freezing point. And that moves us to osmotic pressure. And I'm not going to do a lot with this. Osmosis is the process in which a solvent moves across a semi-permeable membrane. Osmotic pressure is the amount of pressure required to prevent it from happening, okay? Just to prevent it. The more solute particles that are in a solution, the higher the osmotic pressure, the harder it is to keep the liquid from moving across the other side. If I look at the Prezi, there's a, we don't need that one already, or that one. Let's get down to, I'm trying to get to the osmosis picture. I'm close at this point. All right, there it is. Here it is, osmosis. Okay, so we have a semi-permeable membrane that allows like the water to go through. There's the water molecules, and it allows water to go through. And this is the solution side where you have some solid mixed in with the water. The more solid you have, the more it's going to want to push the water towards it because they're trying to make the concentrations the same on both sides. So see, the water level is going down because it wants to fill up this side to put more water on this side so that both sides equal. That's osmosis. So the osmotic pressure is the amount of pressure it would take to push that water back to the other side to keep osmosis from happening. The higher the solvent concentration, the higher the molality or the molarity, the higher the osmotic pressure is going to be. And that's all we're going to do with osmotic pressure. Okay, you did osmosis, I think, in biology. Okay, that's the end of our notes, or the end of the colligative properties. I will see you soon.